Next, the last speaker for today is Pedro Antunes, which is also from the ASAP project, from the work packet 3 mostly, on actually accelerating or working on how we can take the algorithm from work package 2 and implement them on FPGAs, and hopefully have something that is usable in a future space mission. And I believe that's what we're going to hear about now.
Yes.
And he's also a PhD student here at the KTH, sitting mainly in Kista, right?
Yes.
Yeah.
Share the screen.
Thank you for being here.
Thank you for the introduction, Jana. So I'll just start presenting. Today's talk is on the process of inferencing the neural networks in space. For that, we work with FPGAs. So what the challenge that we have nowadays is that the data amount on board spacecraft is increasing, and also besides the data that comes from the sensors, there's also an increase on the amount of satellites in orbit. Just like a survey conducted by Eric Kulu shows the number of launches and the increase, and it also shows how he predicts the future launches, and this has a cost on the amount of data has a cost on the downlink. We can't transfer everything to Earth. We need to compute on board and make decisions on board. But however, the hardware currently on board satellites and the spacecrafts is not capable of inferencing neural networks like we want it to. Our CPUs and GPUs that we commonly use in training and inferencing on Earth are not suitable for space for many reasons. Either they don't have enough performance in the case of CPUs, or they consume too much power in the case of GPUs. And also there's the radiation aspect in space, which also needs to be taken into consideration depending on the mission and the orbit. So our solution is to inference the neural networks on FPGAs. And for that, we're using a high-level synthesis to go from an ONX definition of the neural network all the way to the bit stream with which we program the FPGA. So a little bit of key things to know. An FPGA is a field programmable gate array, and that means it consists of logic blocks and interconnects that are programmable to execute some. So you can program them to execute certain functions, and these logic blocks can be lookup tables, DSPs, flip-flops, which are registers, or VRAM. To program the FPGA, there's many ways to describe the hardware. And what we're using is high-level synthesis, which is a tool that picks a C-like program and transforms that program into a hardware description, so that then we can synthesize that hardware into the bit stream that we can use to program the blocks in the FPGA. A little bit about the current state of accelerators for neural networks on board the FPGAs. There are mainly two architectures. There's an architecture where which is comprised of processing elements, and each of these processing elements can compute different layers of the neural network. They can compute convolution layers, pooling layers, so different operations. And then you can combine different processing elements, and then the processing elements compute your neural network. Another approach is to have a data flow pipeline where you map each layer of your network into the FPGA fabric. Two examples of frameworks that are used to generate these architectures is VT's-AI and Fin. VT's-AI uses an approach about processing elements. It has a DPU engine, and the DPU computes the convolutions and pooling and the various layers on the network. And Fin uses the data flow pipeline approach. They both have its advantages and disadvantages. The data flow pipeline for very deep networks is not as efficient as the processing element, but for smaller networks, it can compute way faster. Another tool that we use is ONX2C, and this tool allows us to convert the ONX model into an initial C version of that model, so that then we can work with it. Our work in here that we're presenting is based on Jonas' work on the data from the MMS mission on from fast plasma investigation, which was labeled by Olszewski. And Jonas defined three network topologies. A baseline topology that is comprised of two convolutional layers and one max pooling layer and two fully connected layers. These convolution layers and max pooling layer are 3D because the data input is 3D. The second topology is smaller. So the baseline is the biggest topology. Then there's the reduced topology that has one 3D convolutional layer, one 3D pooling layer, max pooling layer, and two fully connected layers. And then there's an even smaller network topology that uses only a 3D max pooling and a fully connected layer. So what we did to get the neural networks to inference in hardware, we picked up the network topologies, we defined it in PyTorch, and we loaded the pre-trained weights given by us by Jonas. So we didn't train it ourselves. We don't know how we should adapt the network, but we know how to make the network, this topology on hardware. We then convert the ONX model. So from PyTorch, we export the model to ONX, and we convert the ONX model to C to have an initial version that we can test bench without putting it in our hardware, so that we can easily test bench. Besides that, the data the input data and the labels were converted into a binary file because what we move to the hardware is the binary and not the NumPy arrays and structures. We then created a test bench, a C test bench, to validate that the model works, and this C test bench is a base so is the model then for the host code to connect with the FPGA, interact with the FPGA. So how do we get this was software, but how do we get it into hardware? Well, we tried using VT's AI and Thing, because they're very well-known frameworks, and that they showed very high performance. However, these frameworks don't have support for 3D convolutional layers. Well, VT's AI has support for 3D convolutional layers with kernels of size 1x1, but not other kernel sizes, and we use different kernel sizes. So they didn't work because they didn't support our layers. So our way is what we followed was picking the C code that we generated and massaging it to make with HLS pragmas, that is the tool that synthesizes for the hardware, that understand where it can create parallel sections of the hardware for accelerating inference. Another thing that we did to the models is take the last softmax layer, because the softmax layer is very important for training, because it gives us an idea of the percentage, right? And when you train, you want this layer has to be 100. It's 100%. This output, so it's good for training. But on hardware, the softmax has an exponential operation, and the exponential is costly. And if we don't do the softmax, we still can deduct what's the label by what has the highest value on the output. Then we, after massaging the code, we compiled it with VT's HLS and synthesized it. So the compilation transforms the code into RTL, which is the hardware description. And then with Vivado, we generate the bitstream, which integrates everything into the chip. And based on the C test bench that we created earlier, we created a host program that copies the input to the FPGA, although in a real scenario, the input data wouldn't need to be copied from the host machine to the FPGA. It would be inputted directly into the chip. And we timed the time that it takes to run the neural network only. So what results? And this is very initial results. What I'm gonna. So it's there were, but what's important to notice. Well, first let's look. We can get the number of operations that are executed, and we have the number of parameters of each layer, which is the weights and biases of each neural network, and then we have we can calculate the number of operations that each neural network performs, and the baseline is very computational heavy compared to the other two, and we can see that later on the timing. In terms of resources, we're using very little resources, which is good because it shows us the portability of our implementation. Because we implemented in the Alveo board at FPGA, but with this many resources, there's many other boards where we could implement. And also the reduced resources correspond to a reduced power consumption. And we'll see that later. In terms of inference time, well, for the logic, we can see this gives us an interesting initial view, because for the logistic net and the reduced net, it was very easy to obtain, to map them to the FPGA. There wasn't so, and we very easily obtained a speedup. and also they're very small networks, right? For the baseline net, we would have to iterate more, and maybe instead of having the whole, because the approach that we took is, like I initially said, is the data flow pipeline where we try to put each layer on the network. So maybe for the baseline, another approach using processing elements would perform better. In terms of power consumption, we're on par with the literature. We can try to reduce the dynamic power consumption, but this also depends on the board. And Alveo is a very powerful board, and it is going to have higher power consumption than the others. The total on-chip power corresponds to the line. So it's the dynamic power consumption and the static power consumption. The dynamic power consumption is when you execute the network, when a bit flips, that's going to consume power. And it corresponds, the total on-chip power is both the memory power consumption and the FPGA fabric. The accuracy of our model remains the same as reported by Antunes' work. That is because we didn't perform any quantization on this model, and the weights and biases that we are using are float 32. So based on what we did so far and for the future, what we're looking for is we're going to quantize the network, look at the accuracy penalty or accuracy impact of quantization. We can fine-tune it on the data to try minimize this impact on accuracy, but it will be very interesting to study. We will expand to support other FPGA boards, not just Alveo, because studying Alveo is not used in space, but there are other boards not used right now. It can be used in the future. And besides studying other boards and studying quantization, we're also planning on studying other neural networks and other use cases for space applications. And then with the other use cases, we could look at the platforms, the frameworks such as FIN and VTZI, and compare it to our approach. So, concluding, the smaller and the small size of our networks is a good sign because of power consumption and the portability that it indicates. And this is a network that is using float 32. So if we quantize the data for 1 byte, so 8 bits, it will use a fourth of the memory. Then with the improvement of tools like FIN and VTZI, possibly another flow using HLS, this streamlines the process of inferencing neural networks on board FPGAs and can be extremely helpful for future missions. But yeah, FPGAs with their power efficiency and radiation tolerant are they highly advantageous compared to CPUs and GPUs, right? Because FPGAs are more power efficient, and some have already radiation hardened by design. If you implement one FPGA, it can transfer to others. Okay.
Yes, thank you. Do you have any questions? Have any? Yes, Yuri.
20 watts is a lot.
Yes.
Is there a way to make it
Yes.
smaller?
Yeah. So the Alveo board uses a lot of watts. If you use a more resource, there are more resource efficient and more power efficient boards. But we're gonna try target 5 watts, but that's what is consumed currently. It's what's reported in the literature, and you can achieve that by trying to. You can achieve that in many ways. Sparsity in the network, less because the power consumption ends up, it's how many times a bit flips, right? If the bit flips many times, it's going to consume a lot of energy. So if you have sparsity and we put the weights that are near zero, if you prune them, then that would also decrease power consumption.
Any more questions? Yes.
So we saw these 3 networks, but they are relatively, let's say, light than what we saw in the morning. Apart from softmax, what are the elements that we should avoid, like not having big kernels, not having many layers, not having big feature puffs, but it's your recommendation? I mean.
Yeah, not having the complex functions for activation layers. Like the ReLU is a very good activation layer for inference. Others can be
Big evolution that
yeah.
that we have in the unit, for example. Is it the one?
There are some works of implementing deconvolution in FPGAs. They're not, from what I remember, they're not optimal. They don't achieve very good. But it is possible. It's all a question of the requirements of what do we need, how many frames per second do we need to have, how many, what's the power consumption that we can. But it is possible to implement. Other.
And just the last question, if I may.
Yes.
So we saw huge difference between the 3, huge difference in performance and based on the 3 networks. What was the element that actually was convenient for you based on the baseline and the others?
Yeah, memory access. I think we can achieve way better performance. And the performance that I reported here for the baseline is not the best performance I obtained, but it was the one I took the FPGA resources from. So it was never the best. It was never very good. But I think because if we see the number of VRAMs used from baseline, they use 60 VRAMs. This is the memory for the weights. It's storing all the weights on the onboard the FPGA. These ones use way less VRAMs. They have way less parameters. So
like the kernels were smaller probably, and then the weights were fewer, right?
Yeah.